Can you hear me? Okay. Good afternoon. I hope you are fresh and not tired from lunch. And thank you for the organization of this workshop. It's my pleasure to be here. So in my talk, I want to report about the joint work with Christian Nickelmeier and Greta Panova, who are both here. But of course, the story starts at the beginning, so let me recall what this is all about, even though I'm aware you all know it, but still let me recall. The permanent versus determinant problem. So here we have the permanent, we know it. We have an m by m matrix. The end is our variables. This is the definition of the permanent. How many arithmetic operations are needed to do this? The best known algorithm that we know take exponentially many operations. But the determinant, we all know it, can be evaluated efficiently. And we would want to understand what is the difference. So in all of the talk, I will work in characteristic 0 actually over the complex numbers. Okay, so variance conjecture, we also know that, but let me nevertheless recall it. So Leslie Valiant asked the following question. So can we write the permanent as a determinant of a possibly bigger matrix when the entries are linear functions? So this formulation is the homogeneous formulation. So I have the variables xij, m square variables, an additional variable z, and the entries of this matrix aij are homogeneous linear forms. Okay, then on the left-hand side I multiply with this power of z, so so that this thing will be homogeneous of degree n. So the question is this possible? And well, it's possible, but how big has n to be? It depends on m in order to make this possible. Okay. So it's interesting to know that Polya, a long time ago, looked at this question for n equals m, and he showed it's impossible when it's bigger than 2. Okay. And Leslie Valiant, he proved it's possible if n is exponential in m, and there is this very nice construction by Bruno Gröne showing that 2 to the m minus 1 is enough. I think it's never been formally published, but I don't know, but it's a very nice result. Okay, and the only, yes?
Is it impossible without z?
Without?
Without z?
What is without z?
With homogenization variable z.
Different degrees on the left and right.
Huh?
The question is it
You need
without,
the degrees.
if you leave z, even then is it impossible at n?
Well, without the z, I mean, if you substitute the z by 1, then you get the original phrasing of the conjecture. This is just written homogeneous way. It's completely equivalent otherwise. Okay, the only lower bound we know is 1/2 m squared. This is the result by Mignon-Reser. That's the sad state of the affairs. Okay. And there is this famous variance conjecture from 1979, which states, well, it's impossible to have such a relation star if n is polynomially bounded in M. Okay, we all know that. And we also know that this conjecture is equivalent to the separation of two complexity classes, VP, WS, V and P. Ketan mentioned it, and I don't have to define it. Okay, but we know it's an important problem. It's like the holy grail of algebraic complexity theory. Yes? Sure.
Is there a version of this when I consider so that right side when I have linear forms,
yes,
just linear operator from m by m matrix to n by m matrix. So what is inside of the determinant? It's a linear operator.
Yes.
From m by m matrices to n by m. Okay. So now, is there a positive version of this conjecture? So I only want to do for permanence of positive semi-definite matrices.
Not that I know of. No.
And the operator is completely positive, which goes from M to M.
I don't think there is anything of this kind. I've never encountered it. I don't know. Okay. Last line here, I still have to explain it. There is this implication. If P is different from NP, then it implies VP different VNP. Well, there is a little problem here because here in this model, when you build such a representation, you can use any complex numbers, any complex constants. And somehow you have to eliminate it, and it's possible to do it under the general Riemann hypothesis using a result by Pascal Coirant. So there is this implication. And if you don't allow crazy complex constants here, then you can have this even without. So the lesson is, if you want to separate P from NP, we have to do the separation VP VNP first. Okay, so this is just, okay, this was just the introduction. I assume you know all this. Okay, now let's move on to this geometric viewpoint, which was introduced by Ketan Malmalay and Milin Sohoni a long time ago. So he proposed to study this problem from the point of view of algebraic geometry and representation theory. But one should mention that even before Ketan, there was Strassen in his work on bilinear complexity, tensor rank, where he already realized that the main problem there can be phrased as an orbit closure problem. So it's actually much older, this connection. Okay, so good. Then let's start with the more technical thing. So there is this symbol here, sim n v star. What is it? V is a finite dimensional complex vector space. And then I look at the space of homogeneous polynomials of degree n on V. So functions from V to the complex numbers. So why do I write it in this way? So actually, if you want to technically understand our paper, it's important to have this viewpoint of multilinear algebra. One needs to understand that the space of homogeneous degree n polynomials are symmetric tensors on V star. V star is the dual space. Okay, so I decided to use this notation. It's better not to avoid it. Okay, so then there is the orbit. So in R, yes?
You decided to use it, but these are just homogeneous polynomial of degree n.
Homogeneous polynomial of degree n, functions from V. You can think of it this way, but if technically in the paper it is needed. Okay, this is right. So then, okay, so Avi in the morning he had this notation mg. So the group G, we have a group action here, GLV, acts on the space of homogeneous polynomials just by linear transformation. Okay, and then in Avi's notation, I would have, if I copy this notation, I would have written m sub g of f. So this dot here just denotes the linear action coming from the g. But I didn't want to use the mg because it messes up a little bit the notation. So we get the orbit. So I have my polynomial. I perform all possible invertible linear transformation of the variables. I get the orbit. Okay. Okay. So here concretely, my vector space is the space of complex n by n matrices. So the capital N is n squared. I view the determinant as an element here. It's just the degree n homogeneous polynomial in n square variables. Okay, it's all clear? Good. Now the object that we want to understand and where all the difficulty lies is the orbit closure. So of the determinant here. You can take the orbit closure with respect to Euclidean topology or Zariski, it's all the same by general principles. So, and I like to denote this with capital omega n. It's like, you know, there is the small omega, it's the exponent of matrix multiplication, we don't know it. There's the big omega for the big problem, we don't know it. Like, okay, this is this omega n. So what do we know about it? Actually very little. So omega 2, this is very easy, just to understand the notion. If n equals 2, the determinant is a quadratic form. In 4 variables, it has full rank. Okay, the orbit by linear algebra will consist of all quadratic forms of full rank. If I go to the closure, I get all quadratic forms. So I get here, I would get the whole space of quadratic forms. This is very easy. So if n equals 3, it's already more complicated. There's a paper by Jesko Hüttenhain, is a former PhD student of mine, Pierre Lerre. They determined it, so when you go to the it's interesting to understand what happens when you go to the boundary. What is the boundary? What kind of polynomials you add when you, what are the possible limits? So they proved omega free. This boundary has two irreducible components, and you can explicitly describe it. And for n equals 4, it's already unknown. It's a very interesting problem, and we have a conjecture. I think we know what it is, but the proof is somehow related to some problems related to reducedness of schemes and so. So maybe this can be, maybe omega 4 can be determined, but when n is 5 or bigger, that becomes quite wild a problem. Okay.
So in one sense, when you say known, what do you mean?
I know is known. Okay. I can describe it completely, the boundary.
So
the boundary has, is the union of two orbiclosures, and I can describe it to you what it is, but maybe after the talk. Okay. Good. Okay. So, okay, now the permanent, okay, in this world, okay, I have my perm M, then I do, okay, I have another integer n bigger than m, and now I will multiply this permanent with the power of this linear form x11, and I view it as an element of Dick space. So the point is, in this space on the right hand side there sits the determinant, that n, but m can be much smaller than n, so the permanent is not an element of this space. So one way to make this an element is to multiply with this power of the linear form. We call this the padded permanent. Okay. Right? And there is this conjecture. So I decided to give names to all these theorems and conjectures to make it easier. I want to call it orbiclosure conjecture. I made it up for this talk. So that's, maybe Ketan calls it GCT conjecture. So whatever. So it just states that, okay, this thing is contained in omega n if n is sufficiently big. And this orbiclosure conjecture says this n, the smallest possible n, has to grow superpolynomially. This is the thing. And right, and it's easy to see that this orbiclosure conjecture implies the Welian conjecture. But the that's what Ketan explained to us. It's probably this orbiclosure conjecture is a harder thing, but it seems unavoidable from the point of techniques that we have in mind. So we want to resolve this orbiclosure conjecture. Okay. Right. Any questions so far? So then let's move on to this representation theory. Okay. So I have my group, GLV. It acts on the space of homogeneous polynomials. Okay. Then the next object I will be looking at is the coordinate ring of this thing. So this is a vector space. And what is the coordinate ring, which I denote by this symbol? It's just a space of polynomial functions on this. Okay, so polynomial function taking as inputs themselves polynomials. So mathematically, using this language from multilinear algebra, this is this object, the direct sum over all degrees d, sim n. So this is the object. And this object here is called a plethysm. Okay, so this is a plethysm. And good. So I view this as a module over this group G, and we know GLV is a reductive group, which means that every finite dimensional module is a direct sum of irreducible ones, or maybe I should say representation. So this somehow splits, and this is also known that, I hope you know this, that the irreducible GLV module, in a way we understand them, we can classify them. They are called Weil modules, and they are parameterized by partitions. Okay, partitions, and it turns out, okay, maybe the next here is a partition. Okay, an example. A partition 531 is a decreasing sequence of integers. Usually it's written as a diagram, so the 5 I encode in this way. I have a row consisting of 5 boxes, then a row consisting of 3 boxes, here 1 box. So I think of the partition as a diagram, as a Young diagram. And what we know here, the while modules occurring here must be labeled by partitions of size d times n. I should define what is the size. The size, written with absolute values, is just the number of boxes. Okay, it is known that this must be a multiple of, must be d times n. The length of the partition is the number of rows. Okay. And what we also know, this thing, the number of, so the length of the partitions that occur here is bounded by the dimension of the group, which is n squared, by general principles. Okay. Right. So it always takes a long time to explain the setting when I talk about these things, so please stay with me. C omega n is the coordinate ring of my orbit closure. Okay, now the idea is, what is the idea? Okay, so how can we understand this coordinate ring? So here is a simple thing. So I just look, I make a restriction. I have the big space, is the space here of the homogeneous sim n v star. And I can just restrict polynomial functions on it. I can restrict to omega n. So this gives a surjective homomorphism, which is equivariant. Okay? So I can view this as a homomorphic image of this polynomial ring. And then I will say, okay, and this is a very important notion for the rest of the talk, I say a partition occurs in the coordinate ring of omega n if this thing contains a copy of this while module. Okay? Okay, a lot of notation, I know. So now let me explain what is an obstruction. Okay, and I do it in the context of the permanent. So I play the same game with the padded permanent. I have the padded permanent here. I look at the orbit closure. This now depends on 2 parameters, n and m, and I just denoted z and m. Okay? And then the strategy, what do we want to do? We want to show actually that this padded permanent is not contained in omega n. So let's assume the contrary. Let's assume it is contained. Then, of course, because this thing is invariant, I can conclude if this is the case, then the z and m is contained in omega n. So I have this containment of orbit closures. Then I go to the coordinate rings, and I get a surjective ring homomorphism, which is equivariant. And then I use Schur's lemma. So I think of these spaces now, I decompose them into irreducibles. And then I notice by Schur's lemma, if lambda occurs on the right-hand side, it must have occurred on the left-hand side. That's the very general principle. Okay? And the partition lambda violating this condition is called an occurrence obstruction. That's what we are looking for, occurrence obstructions. Okay? Okay? If I have an occurrence obstruction, then I have proof that z and m is not contained in omega n. So this was the plan. I should notice here at this point that Schur's lemma actually gives more information. It gives an inequality of multiplicities. Okay? So, but I will not discuss this any further. Okay, well, a partition violating this inequality is a multiplicity obstruction. So Christian in his talk, he will elaborate on multiplicity obstructions. Okay. So the main result, what is the main result of the talk? So there was this conjecture in GCT1, GCT2, I don't know, by Ketan and Milind. I call it occurrence obstruction conjecture. You read it for yourself, but basically it says one can resolve the orbit closure conjecture by means of occurrence obstructions. Okay, so this was the hope. And by what I explained right before, using Schur's lemma, the occurrence obstruction conjecture implies the orbit closure conjecture. Okay? And the main result is of this paper, unfortunately, the occurrence obstruction conjecture is false. So this is the theorem with Christian and Greta. So maybe let's have a look at it. What does it say precisely? So I have my parameters n and m. So let's assume n is greater or equal to m to the 25. Okay. Then I take any lambda, the size should be a multiple of n, let's say n times t. Then if lambda occurs in the coordinate ring of z and m, then lambda also occurs in the coordinate ring of the determinant. So, hence the occurrence obstruction conjecture is false.
Permanent here is special?
Sorry?
Does permanent here is special, or you can
I'm going to discuss this, yes. Okay, just patient. Okay, first let me mention that before this paper there was another paper by Christian and Greta. They had a similar result which said that the orbit closure conjecture cannot be resolved via Kronecker coefficients. So I don't have time to go into this, it's another story, but yeah. There was this result before which already contained many of the ideas of the proof. Okay, and now, right, I will discuss this before I talk about the proof. Let me discuss what this actually means. Now, our proof, yeah. So let me discuss, you will see that, one can have, okay, one could have the following idea. Instead of thinking about the permanent versus determinant, one could also think about other complexity measures. Let's have a look at the so-called Warring rank. What is the Warring rank? Or symmetric tensor rank. I have a polynomial P, a homogeneous polynomial. Then it's known, I can always write it as a sum of powers of linear forms. It's known, and the question is, what is the minimal number of terms? And this is called the Warring rank, or symmetric tensor rank. Now, I think it is quite well known here that one can actually prove exponential lower bounds on the Warring rank of the determinant and the permanent using the partial derivative matrix. It's in a paper by Noam Nissan and paper Avi, and I think this is quite known. So then the question is, can we prove such bounds on the Warring rank by obstructions? Let's have a look. So one way to see it is the following. Let's take this power sum here. Yeah, the x1 up to xn squared of the variables, and I have this thing. So what I do now, I replace the determinant by this power sum. Okay, and then I play the same game. I take the orbit closure. Let's denote it like with PS, like power sum. Okay, and then, okay, what do? Then we ask, can we somehow prove with our methods that the padded permanent is not contained in this? The corollary is this, and I thank Avi for pointing this out. It comes out of the proof. The statement of this corollary is basically the same as for permanent versus determinant. You read it for yourself. What does it say? You cannot separate using occurrence obstructions. So the strategy of occurrence obstructions cannot even be used in this weak model of the PSN against padded polynomials. Even more, I mean, that's what I've written here. So what I have done here, I have replaced the determinant by the power sum. Much simpler polynomial. This is the determinant. How about the permanent? Now this is the question by Klim. Is it important? Well, no. You can replace the permanent here by any homogeneous polynomial of degree m in m squared rebus. Any. You have the same thing.
padded, right?
Because of the padding, yes, exactly.
Because of the padding. Yeah. This is, yeah. So in a way, it's a very strong result of weakness of the method, or I don't know how to phrase this.
So where is the padding? Because like this is a homogeneous model, so.
Yeah, but it's.
The padding is adding a power of a variable to the missing degree.
Okay, but when he says that whenever you can, because you don't need to pad in this case. But
not necessarily. You're right. It's not necessarily, but
the obstruction, the corollary is for the padded version or any version.
Sorry,
So So you're saying the permanent, when you say the permanent in this example, are you
Okay,
talking
I
about
mean, what I'm saying is the Z and M I defined before. It's the orbit closure of the period permanent. I can replace it by the orbit closure of any homogeneous polynomial of degree m in m squared variables. Just replace the permanent by anything. But do the padding. This is essential for the proof. Okay. Probably I'm using up too much time. So now in the next part, I want to outline the proof. What are the ingredients? Okay, the proof is quite tricky.
Multiplicity abstractions can work here, or you don't rule it out?
I don't know. So I don't say anything about it. So, okay. So if you want to read the paper, so we have a section 2 with an overview of the proof, and I think it should be quite accessible. And I'm trying to explain what is in this overview of the proof. So the first ingredient is an observation going back to Kadish and Landsberg. So what does it say? So I have a diagram given by a partition lambda. Then I can remove the first rows, and then what I get, I will call it the body. I call this the body of the diagram. And I denote it by lambda bar. So this is the thing. Okay. So then Kadish and Landsberg, they noted the following. So let's assume some lambda here occurs in the coordinate ring of Z and M. Okay, then two things hold. First of all, the length of lambda, which is the number of rows, is as low as m squared. This was known before. Second, the body of lambda is has size at most md. So it has a small body. Think of n being much bigger than m. That's what we had in mind. So this condition here, that the body has most this size, is equivalent to saying that the lambda 1, the first row, is at least m minus m times d. So it means the lambda has a very long first row. Very long first row, a little bit of body and not many rows. Okay, so this is
a consequence of the padding.
This is a consequence of the padding. It's a very strong assumption. And this is a main ingredient of the proof. Okay. So, and this is the only information we exploit about the orbit closure of the padded permanent. So you can, yes?
So if you pad it differently, suppose you didn't add a variable, but you just put diagonal copies of the permanent n over m times instead, right? Then the proof doesn't work. You cannot rule out a reduction via occurrence obstructions.
It's very important to have this power of the linear form.
Yeah, so you don't know, I mean, but that's a very natural question
Yes.
to ask.
Yeah, so what would you...
Put the permanent n over m times diagonally and ask whether this reduces via linear transformations to determinant. You cannot rule it out even via occurrence obstruction.
Yeah, I would have to think about... doesn't come out of this argument. So, good question. It's a good question. It's a good question. Yep.
Yeah, it seems that dependence on the form of padding is...
Yeah, it's very relevant. It's very relevant for the proof. Maybe this can also be excluded, but this would need some thinking. Okay, so as I said before, I can then replace the permanent. And maybe I should also mention that this Kadish and Landsberg property was also crucially used in the paper by Christian and Greta. So, okay, second ingredient, very general, is the so-called semigroup property. So somehow, in order to prove the theorem, we need to show for many lambda that they occur in the coordinate ring of the omega n. So how do we do this? The strategy is that first we establish for certain shapes of lambda that they occur, and then we combine it, and the combination works with the semigroup property. And here is the semigroup property, just says if lambda occurs and mu occurs, then lambda plus mu occurs. And the proof is very simple. If you know about highest weight vectors, you have a highest weight vector for lambda, highest weight vector function, say, one for mu, just take the product. For those who know. So it's not a difficult thing. Okay. This property was used in the paper by Greta and Christian.
What's the plus operation here?
It's addition, so meaning, okay. If you think of the partition is a tuple, then it's the addition component-wise. Okay. Okay. So what are the base? Okay, now I have to tell you what are these basic building blocks. Okay. Good. So there comes the connection to the invariant theory. So I'm thinking of, as a diagram, I will take a rectangle that I possibly extend. So maybe I have the rectangle, but then I have maybe a longer first row. So there is this notation, which is not to k times L, stands for the diagram, k times L with k rows of length L, to which a row has been appended, so I get a total of nk boxes. Okay, here is an example, 3 times 4, you can see it here, the rectangle, and then I add a couple of boxes here in the first row. Okay, so then I have the following result. It will be an ingredient. I call it propositioned row extended rectangles, and it says the following. Whenever the L is even and N is greater or equal K times L, then this diagram occurs in the coordinate ring of omega n. Okay, always. Okay, and I will tell you later on the idea of how we prove this. So these extended rectangles always occur if n is sufficiently big and the L is even. Okay, and actually now here I can also explain the connection to the power sum, because how do we prove this? The only property of omega n that we use for proving this proposition is that the omega n contains many padded power sums. Okay, and this follows, here is the proposition, from the universality of the determinant. So I wrote it here as a proposition. Okay, so what do we have here? X and phi 1 up to phi k are linear forms. So I take here a power sum, then I pad it. Okay, and the statement is this thing is contained in omega n if n is greater or equal sk. And what is behind is just this insight, going back to Leslie Valiant, saying that if you have a polynomial and the formula size is, say, strictly less than L, you can get it as a projection of an L by L determinant. Okay? Now you just see that this thing, the formula size of this thing is easy to control. That's all. Okay? Right. So, good. So now what is the strategy of the proof? Okay, so I only will talk about the case where lambda is even, meaning that all of the components of lambda are even. So all the row lengths are even numbers. Okay. So I have such an even partition. N is greater or equal m to the 25. I know that lambda occurs in the coordinate ring of Z and M, and I want to show it occurs here. So how do I do it? First step is the Kadish Landsberg observation, which I have reproduced here. Second step, there are two cases to distinguish. Case one is when the degree is large. So the d is the degree, okay, I call this the degree, let's say greater than this. So if the d is large, then we do the following, as in the paper by Greta and Christian. We remove the first row of lambda. So then I get the body. And then I decompose the body into a sum of even rectangles. This is very easy, so just cut it. Okay. Then you see for each. Okay, but this decomposition of the body, I have to get back a decomposition of the lambda. And this is possible if the first row of lambda is sufficiently large. So this involves some calculation. I don't want to do it. But I wrote it here. I can write actually lambda as a sum of row extended rectangles because n and t are sufficiently large. And then I apply this proposition row extended rectangle. I know all these extended rectangles occur in the coordinate of omega n. I apply the semigroup property and I see that the lambda occurs. Okay? So that's the idea. Okay. This is case one. And how about case 2? Case 2 is the harder, I believe. If the degree is small, then what do we do? So we have another result. I called it all. I don't know, couldn't figure out a better label. That's the proposition all. What does it say? Now I have a partition. Again, I have a bound on the size of the body, and I assume m d squared less than or equal n. Okay? Under these assumptions, the proposition says every highest weight vector of weight lambda, I will define what it is, but every highest weight vector of weight lambda in the plethysm, viewed as a degree d polynomial function on this space, doesn't vanish on omega n. Every. In particular, if lambda occurs here in sim d sim n, then it occurs in the coordinate ring of omega n. Okay, so this is the statement of this proposition. Okay. So the proof of this proposition, what is behind? Well, we had to develop some insights regarding plethysms. I think these are new mathematical insights, so I would call it lifting highest weight vectors in plethysm. Okay. And it is related to the known stability properties of plethysm. So I hope I have time to explain a little bit what is behind this. Okay. Okay, yes. This was all for the case of even partitions. If I have general partitions, we need, there are two things. We need more building blocks. So far I had a rectangle with a extended first row, but for the general case, we also need to extend by column. So you have, and more tricks. I mean, it's a bit more complicated. I don't want to go into it. Okay, so this was the strategy. Okay, now let me go a little bit more to the details. So it has a lot to do with invariant theory. But first, let me define what is a highest weight vector. I used this word already several times without defining it. Now I want to define what it is. So how can we show that lambda occurs in this coordinate ring of omega n? Okay. So we do it via highest weight vector. So what is a highest weight vector? So in this context, so it will be an element of the sim d sim n. And the property is, well, instead of looking, I have the action of the group GLN. But now I will go to the subgroup of upper triangular matrices. Okay, and actually I want to have two properties. I can go to the subgroup of upper triangular matrices where there are ones on the diagonal. It's called unipotent group. And the first condition is my F should be an invariant under this group, under the unipotent group. But also, I want to have this nice property with regard to the action of diagonal matrices. They can be all combined by this formula. So I have here an upper triangular matrices. The T's are on the diagonal. I act, on F. And what I get is a multiple of F. Okay. And right. So in a way, I say the F is an eigenvector of the. I have the collection of all these linear operators. Each upper triangular matrix gives me an operator, and F is a simultaneous eigenvector for all of this, and these are the eigenvalues. And they depend. Okay. The definition. Now you see, special case, if the lambdas are all equal, okay, then what I have here is the product of the T's in parentheses to the lambda 1, but the product of the T's is 1 because when I assume that the determinant of this matrix is 1. So F is invariant under the action of upper triangular matrix of determinant 1 if this holds. And okay, with a little bit more theory, one can show if all these lambda are equal, it's even invariant under the full SLN. Okay, yes? 5 minutes, okay, I have to run. Okay, right. Okay, now I view my F. I hope, okay, there's another important, it's hard to explain. This thing here, okay, this symmetric tensor I view as a homogeneous polynomial of degree n on this space. And the essential observation is if f evaluated at p is non-zero, then lambda will occur here in the coordinate ring of the orbit closure. So this is the strategy. I don't have time to explain why. Okay, but then let me go quickly to, what are fundamental invariants? The question is, what do we know about the invariance of this space here? There is a result, you can go to how, saying that if t is less than capital N, there are no non-zero invariants. But if t equals n, there is exactly one SLN invariant, exactly one, up to a scaling. And I like to call it the fundamental invariant. It was already known to Cayley. Okay, Cayley already had found this, some hyperdeterminant. So and I can write down what it is. Okay. So I view this invariant as a homogeneous degree n map. It goes from here to here, and then what does it do? Okay, so I evaluate my f at this polynomial, which I have written as a symmetric tensor. So I write it this way, and this is the coefficient tensor, is a symmetric tensor. Okay, and then it looks like this. So if you see, okay, I'm a little bit short of time, but you see it looks a little bit like determinant. Okay, it looks a little bit like a determinant, and actually there are two things. The first thing is it is an invariant. It's this wonderful property. F of g applied to p equals fp multiplied by this power of the determinant. And if n equals 2, actually this specializes to the determinant up to a factor. Okay? This is easy to see. So then what we do, how we use this? So I mean, how can we establish the existence of these spacing building blocks? Well, what do? I take this f, I try this, and I try to evaluate the p and try to show it's non-zero. But it's harder than it might look. So here is an example. There you see the problem. So let's take the special case fnn, this thing, evaluate at the product of variables. Okay? Then if you check this out, it's easy. Then you realize what you get is this. The number of column even Latin squares minus the number of column odd Latin squares, whatever this is. Okay? You have to show this is non-zero. Actually, sorry. This is a typo. And okay, we want to this. I wanted to write here non-zero. It's open, and this is an unknown conjecture in combinatorics. It's called the Alon-Tarski conjecture. Alon-Tarski conjecture is combinatorics. It says if n is even, that the number of column even lattice squares differs from the number of column odd lattice squares. So even in this very simple case here, we don't know the answer. Okay, just in special cases. So what we did then, how did we save this? It's the following observation. Instead of taking this product of variables, let's take the power sum. Now, if I have my fnn, my fundamental invariant, I evaluate at the power sum, I can prove it's non-zero. The way this is done, I mean, you look at what this means, and fortunately, all the signs get plus, so in a way you have a sum of squares and you can prove there's no cancellation. So actually this idea of doing this is, we did it first in a paper with Matthias Christandl together. So this is one, you see, one technical tool where we, yeah. Okay, I'm almost done, okay. Okay, now it's getting, few words about the lifting. Yes, there was this complicated proposition, and I don't have time to explain anything because I'm over time anyway, but mathematically what we added here was we constructed a lifting map. So from sim d m to sim n, so you see this m gets bigger. So we constructed a map, a linear map, somehow, I don't have time to explain all the details, which had many, okay, what were the properties? So this map, kappa, maps highest weight vectors to highest weight vectors. And what we also did, we came up with a list with a generating system of these representations. So the generators are labeled by certain tableau, VT, and then we could explain what happens under this map. So the VT goes to a VT prime, and we can combinatorially describe how you get T prime from T, which is a very nice and clean description. It's very combinatorial. Yes. Okay, I'm almost done. Okay, right. So, okay, maybe I can say it was known in combinatorics that these dimensions under certain constraints, the multiplicities do not change when you go from here to here. But for our proof, it was, what is the new ingredient mathematically is the description of the highest weight vector. So you have more information on these plethysms than were known before. This was essential for our proof. Okay, and I think I skipped the proof of the proposition. It was too complicated. I was hoping I could go through the proof of this proposition, explain it, but it's too hard. So then I think I stop here, and you can ask questions. Thank you.
Okay. Could you please get back to that Kelly formula?
Kelly.
Yeah.
Yeah, the wonderful invariant.
Okay.
Okay. That one.
So here's the story.
Our story.
Okay. So this is actually what I call quantum permanent.
Aha.
So now that there were like several ways to write that proof of that scaling algorithm, operator scaling algorithm, Avi, myself, Ankit, Raphael. Okay. One proof is to use capacity. Okay. I also get the proof which used that thing. Okay. What is the idea that of operator scaling uses thing? So this thing is responsible when you have 4 indices for polynomial identity checking. Okay. This was the invariant actually which started all that operator scaling. This was quantum permanent. Okay. Okay. So now what is the proof of that? You do lift. You take this tensor and at some point that lift using Darkson makes the thing positive, and that and because it's integer it will be, so anyway it gives the bound on the capacity, okay? So anyway essentially the proof of that algorithm is combining combining this one with lifting.
So you are saying
what I'm saying is that there is very deep connection between what is happening there and here.
Yeah, I understand. You are saying in the analysis of your algorithm, in your paper, you use this invariant for the analysis.
This was what I call quantum permanent.
Okay.
Did you know about Cayley's thing?
No, actually it has many names. This thing actually it's called Pascal hyperdeterminant.
Who calls it Pascal Hyper? Okay, I know it's...
Somebody who is like Pascal.
Let's take some questions.
Okay, yes, okay. Thank you.
Okay, one quick question.
So maybe I have a question, which is, so here you were actually saying not just that the permanent is hard, but basically under this notion, you're not going to get occurrence obstructions for any function.
Any padded.
Any padded.
I mean, in this way. So I'm curious now, if you're starting to looking at multiplicity obstructions or GCT in general, is there a general way by which you can say that the random function is hard?
Yeah, that's a very good question, and I don't think that. This is the most natural thing. We know the lower bounds on generic forms and generic tensors. But I don't think so, because this can only work for those objects that are characterized by its symmetry group. So, but if you have a random object, it's not characterized.
No, you don't need the permanent to be. You need the determinant. You don't need the permanent.
No, I think his question is, can we?
You didn't use the symmetry of the permanent,
No.
did you?
No. You didn't use the symmetry of the permanent. I think the question is whether GCT approach is complete. Let's say with multiplicity. That's the question.
Yeah, with multiplicities.
Can you
But I
prove
understood-
existential lower bound.
But his question, Madhu's question is whether can one prove a lower? I try to see whether I understand your question. Can one prove using GCT a lower bound on generics, random functions?
Right.
So, as far as understood, your answer about polynomial, when answer is no, at least for occurrence abstractions.
Well, in this padded setting, it is padded setting. I mean,
I work with padded things, just
When it's not.
but I want to know if it's. But you could go to multiplicity abstractions, and it's. The answer is
I think for multiplicity, we know very little about multiplicity abstraction, but there is a result. Probably Greta will talk about this. What we can say when there is no padding. Okay. Hopefully.
We'll see tomorrow.
We'll see tomorrow what happens.
Let's take all other questions offline and
Yes.
like shorter break and we'll be back.